Okay, welcome everyone. Very happy to have you here. Let me first say very few short things about the Zoom etiquette, the etiquette on Zoom that we're trying to follow here. I would like to encourage everyone to use their real name. I think it's mostly the case, so thank you very much for that. Also, please have your videos switched on and your microphones switched off. The microphones switched off is better for the bandwidth, and the video should not be a problem for it, but it creates a more sort of a atmosphere of actual human interaction. So if you don't mind keeping the videos mostly on anyway. If you would like to make a comment or ask a question, please either use the raise your hand function in Zoom, which is in the right panel if you open up participants and chat, or just say so in the chat that you have a comment or a question. If you have a finger, sort of a follow-up on something that somebody has asked, please say so in the chat. Okay, now you should know that this seminar is live streamed on our YouTube channel, Beyond Spacetime YouTube channel, and will be recorded and made available on that channel later on. Okay, with that out of the way, let me introduce Nora Boyd, our speaker today. I'm very happy to welcome her here today. She's an assistant professor of philosophy at Siena College in New York State. She did her undergraduate in physics and in philosophy at the University of British Columbia and an MA in philosophy at the University of Waterloo. She then moved to Pittsburgh, to the University of Pittsburgh, to do a PhD in the history and philosophy of science. But in between degrees, she's worked as a research scientist at the University of Washington on different projects in physics, mostly related to particle physics. So projects determining neutrino mass or a search for dark matter candidates and projects like this. She works in general philosophy of science and in philosophy of physics mostly, where the physics she looks at are astrophysics and cosmology. Those philosophical questions she's particularly interested concern the philosophy of the experiment and the relationship between theories and experiment and data. As I'm sure we'll hear today, so the nature of scientific evidence, questions like this. But she also has AOCs which are not so directly related to her core areas in the history and philosophy of the environmental sciences and climate science, but also in the philosophy of psychiatry and biomedical ethics. She has, I believe, a forthcoming book with Cambridge University Press on the epistemology of experimental physics. I'm very much looking forward to that. And I've read in her CV that she knows how to operate machines like a drill press and a bandsaw. I certainly could never put that on my CV because I once lost this finger almost operating a bandsaw. So you really need, I have a lot of respect for people who can safely operate machines. Okay, good. So I'm very happy to welcome her here today. She will be talking about observation and intervention are irrelevant to empirical science. Please, Nora.
Thank you so much, Chris. And thank you for inviting me to give this talk. I mean, in pandemic times, so much has been canceled. That I really appreciate the opportunity to share work at this point with friends and new faces and in this really awesome venue. So thank you. So empirical science has long been closely associated with observation and experimentation. Indeed, it's perhaps tempting to define empirical science as investigation of the natural world via the methods of observation and targeted intervention in controlled experiments. However, the historical and conceptual affinity between empirical science on the one hand and observation and intervention on the other has led to some serious linguistic contortions. So to accommodate research in which human eyeballs play little, if any, significant role, and detectors that receive information without intervening, some have been tempted to stretch these terms, observation and experiment, to fit unintuitive cases. So for instance, to make sense of the linguistic practice of physicists who were happy to call the tank of dry cleaning fluid deep in a gold mine in South Dakota used to detect the solar neutrinos in the 1960s, an observation of the interior of the sun. Dudley-Shapiro argued for an inclusive characterization of scientific observation, according to which X is directly observed if, 1, information is received by an appropriate receptor, and 2, that information is transmitted directly, i.e. without interference to the receptor from an entity X, which is the source of the information. And using this account, and by explicating the release of information from the source, the transmission of information, and the receptor of that information for the case of the Homestake neutrino experiment, Shapiro argued that we can sensibly regard this research as direct observation. To take a different example, the language of observation and experiment has cropped up in reference to computer simulations. For instance, the simulation of cosmic structure formation. So philosopher Stephanie Ruffy cites a curious instance of observation talk applied to cosmological simulations from the condensed matter physicist J.S. Langer, who says, the computer literally is providing a new window through which we can observe the natural world in exquisite detail. And perhaps these examples strike you like they strike me as counterintuitive, if not outright misleading. Is it really useful to call a neutrino detector an experiment for direct observation, or to speak of a computer as literally providing a window for observation of the natural world? So puzzling cases like these raise the following questions. Are observation and experiment core characteristics of empirical science? And if not, what is? So I'll argue that observation and intervention are relevant to the empirical nature of scientific evidence, and hence for its epistemic utility in learning about natural objects, systems, and their processes. What matters, instead of whether the evidence in question is gathered by observation or intervention, is that the evidence derives from a causal chain that has one end anchored in the worldly target of interest. And to arrive at this conclusion, I'll make two sub-arguments. I'll first show how invoking a dichotomy between observation and intervention and failing to track instead the distinction between the empirical and the non-empirical leads to three mistaken inferences about astrophysics, which I think are themselves just kind of instances of more general, equally mistaken inferences. And second, I'll argue that ignoring the observation-intervention dichotomy and instead attending to the distinction between the empirical and the non-empirical yields deeper and more interesting questions about the epistemology and methodology of science. And again, drawing on some cases from astrophysics. So let's consider three theses that rely on this contrast between observation and intervention, which I'll reject, and then I'll explain how and why I think we ought to sidestep the whole issue. And towards the end of the talk, I'll return to some cases on which to test the fruitfulness of this approach. So the first thesis that I'm going to reject is that astrophysics, along with astronomy and cosmology, is a distinctly observational science, since its targets are too distant to experiment on. And there are two main reasons that I reject this thesis. One is the general point that much contemporary science, including astrophysical research, is conducted with sophisticated instrumentation and detectors, while the word observational, both linguistically and historically, still connotes perception with human senses, specifically sight. The second is that observational science here is contrasted with experimental science, that is, with intervention. It relies on the idea that a distinctly observational science is precisely one that fails to be experimental, one in which intervention on the target system is impossible or otherwise absent from that practice. So as an example of someone stating this thesis in print, I'm going to pick on a friend, philosopher, astrophysicist, and journalist, Sabeel Andrel, who in an article on philosophy of astrophysics writes, astrophysics and cosmology share a common problem in that they both need to acquire knowledge of their objects of research without directly interacting, manipulating, or constraining them. But in construing astrophysics in this way, this thesis sits uncomfortably with research like the quote unquote laboratory astrophysics advertised by the Harvard-Smithsonian Center for Astrophysics, laboratory-based dark matter experiments such as that my friends at the UW are doing, the Axion dark matter experiment, laboratory-based nuclear astrophysics, and an example that I'll return later to in detail, laboratory-based investigation of hydrodynamical instabilities of the sort thought to occur in supernovae. So how should we make sense of these astrophysical experiments, these examples of laboratory-based astrophysical research? If astrophysics is distinctly observational, like astronomy, then it would be wrong for these researchers themselves to count these experiments as part of astrophysical research. But there is a relatively non-misleading way to make sense of this research as properly belonging to astrophysics, namely reject thesis 1. So the second thesis that I want to reject is as follows. Astrophysics invites the use of simulated data in the place of experimental data, since its targets are too distant to experiment on. And I suggest that philosopher of science Margaret Morrison holds this view. So here's a quote. There are a variety, says Morrison, of contexts where computer simulations do take center stage as the source of experimental knowledge, simply because the systems we are interested in are inaccessible to us. An example is the evolution of spiral structure in galaxies. Because the typical time and distance scales are so vast, the only way experiments can be performed is by simulating the system on a computer and experimenting on the simulation. In the astrophysics case, Morrison says, we may want to say that simulation is an acceptable source of experimental knowledge simply because we aren't able to conduct materially based experiments in the way we can with other types of systems. So Morrison's thought here seems to be that, insofar as we can't experiment on astrophysical objects or systems, but we can, in a sense, experiment on our model astrophysical systems by running simulations, then we can substitute simulated data where empirical data would have been used to generate astrophysical evidence. But this logic just seems wrong. It sounds like, given that you don't have the thing that you really want, substitute something different and use that instead. But surely whether or not the proposed substitute is apt for the purpose matters to the prudence of this strategy. And simulated data lacks the relevant feature of data generated by experiment in this context, namely, having been produced by interaction with the worldly target. The third thesis that I want to reject is that astrophysics is not properly scientific at all, since intervention is characteristic of properly scientific methodology, and its targets are too distant to experiment on. So I think this thesis is expressed in philosopher of science Ian Hacking's super fun 1989 article, Extragalactic Reality, the Case of Gravitational Lensing. If you haven't looked at this recently, highly recommend it. This is the article where he says, quote, galactic experimentation is science fiction, while extragalactic experimentation is a bad joke. He says the method of astrophysics is the same as that of astronomy in Hellenistic times. Model, observe, and remodel in a way that saves the phenomena. And natural experimental science is a matter not of saving phenomena, but of creating phenomena. But in astrophysics, we cannot create phenomena, we can only save them. And so astronomy is not a natural science at all. And since astrophysics shares the method of astronomy, astrophysics is also not a natural science at all. So this view of natural science is clearly too restrictive. Experiment, interference, and creation are not necessary for properly scientific research. Hacking draws the line in the wrong place. And perhaps here he is being intentionally hyperbolic, since elsewhere he couches the connection between intervention and the properly scientific more gently. Nevertheless, the right question is not whether there is properly scientific astrophysical evidence at all. So at least part of what has gone wrong with these three theses is that they all rely on a contrast between observation and intervention. Astrophysical evidence is not, strictly speaking, observational. Some of it involves intervention after all. And regardless, what makes for the epistemic utility of astrophysical evidence is not that such evidence is derived from observation, that it fails to derive from intervention, or vice versa. Observation and intervention are irrelevant to the empirical nature of astrophysical evidence, and I believe to the nature of empirical evidence broadly construed. What does matter is that the evidence derived from a causal chain that has one end anchored in the worldly target of interest. That is, data, including astrophysical data, are empirical with respect to some target when there is an interpretation of the provenance of those data using the resources of some epistemic context, such that the data are products of causal interaction with the target. So an epistemic context, in the sense I intend here, is just a collection of conceptual, theoretical, and representational resources from the perspective of which the data is to be interpreted. And it's important to note that the data are empirical relative to a target. Without specifying a target, it's impossible to say whether some particular data set is empirical or not. Data are also empirical relative to an epistemic context, and the epistemic context supplies the resources with which the data are interpreted. Data never speak for themselves, but rather always require interpretive resources. In particular, background theory to furnish a causal story, connecting the worldly target of interest to the data collection and recording process. And if you'd like a more thorough explication of, defense of this idea, I have a paper titled Enriched Evidence that was published in Philosophy of Science in 2018 that I will take the opportunity to shamelessly plug at this time. So an important feature of the view of empirical data that I'm defending is the causal production of data. And as I said, to be properly empirical, data should have been produced by causal processes that connect the worldly target of research to the process of data collection and recording from the perspective of the epistemic context in which the data are interpreted. There is no perspective outside of an epistemic context from which the causal process can be identified and traced. And indeed, there's no perspective outside of an epistemic context from which a worldly target can be identified in the first place. Yet, using the resources of an epistemic context, it can be possible to answer the following question. Were these data produced by causal interaction with the target? And this view of what makes data empirical obviously relies on the notion of causal interaction, which for philosophers is a notoriously fraught notion. Right? And I'm not committed to a special theory of causation or causal interaction here. In fact, I believe that this view of what makes data empirical is probably compatible with a wide variety of ways of explicating the notion of causal interaction. And I think that it's best that the precise explication of what counts as causal interaction be spelled out from within the particular epistemic context that's furnishing these stories, using the resources of that background theory in play. So why is it important for their empirical character that data be connected to causal processes, data be connected by causal processes to worldly targets? Why is this important? One important reason in support of this approach is that if one does not require the causal production of data, one risks collapsing the distinction between empirical data and virtual data. The products of models and simulations can have relationships to worldly targets, for instance, standing representation relations, without having been produced by those targets. I think we want to be able to keep track of these differences. So to see why causal production matters, let's consider a characterization of what makes data empirical that eschews causal production and relies instead on ostension. So this view suffers from a serious drawback. It's not easy to see how it could be applied to data sourced from faraway worldly targets that no one can point to in an act of ostension. So the characterization I want to consider comes from this insightful and philosophically valuable paper by Matthias Kaiser from 1991 titled From Rocks to Graphs, The Shaking of Phenomena. And in this paper, Kaiser develops an abstract characterization of the epistemological structure that carries scientific reasoning from what he calls observable reality or data to empirical phenomena. And the basic elements of an instance of this structure are an anchor point and an inference ticket, and inference tickets for Kaiser. And roughly the anchor point is the bit of the world that source the data, and the inference tickets transform the data by redescription and other operations licensed by theoretical resources, either via bootstrapping or the incorporation of accepted background theory, which might include incorporating data collected in other contexts. And although Kaiser goes on to formalize these intuitions, so anchor point becomes zero structure and so on, the gist of the idea is as follows. The zero structure consists of the objects of scientific inquiry, this is a quote, together with the simple active presentation. Kaiser says, my basic intuition here is that that scientific data rest on raw material that can be presented or reproduced upon request. It is essential that this level be kept as simple as possible, e.g. this rock here, or these spots on the screen there, or in the social sciences, these filled in questionnaires, etc. So the zero structure contains all of those things that are to be subjected to scientific scrutiny, i.e. that are to be measured, weighed, radiated, diluted, accelerated, etc. So thus, on Kaiser's view, what makes data empirical are these original and reproducible acts of ostension, like this rock here. And as I hinted above, I believe that Kaiser's view is ill-suited to faraway targets in virtue of this feature of his account, right? On this account, when the material specimen is not present at hand, the scientist cannot anchor data, cannot anchor the data to it via acts of ostension like this rock here. Instead, on this account, she is forced to anchor her data not to the worldly target of interest, but to some intermediary, as in these spots on the screen here. So let's consider an example of this sort. Here's a visualization of data from the Arecibo telescope, RIP, displaying spots that can be interpreted as radio signals from distant galaxies. And on Kaiser's account, what makes the data visualized here empirical is that they can be picked out by ostension, by some scientist gesturing to the image, these spots on the screen there. This approach locates the empirical at the site where some bit of the world is present to the perception of the human inquirer. In this case, the spots in the image are what is present to the inquirer. But this approach seems to miss the point. The data displayed here are empirical with respect to galaxies. They are data encoding the radio frequency emissions of galaxies over time in virtue of being produced by the interaction of electromagnetic radiation emitted by those galaxies, traveling through space and interacting with the receiver of the observatory, of the Arecibo Observatory Telescope, and subsequently all the rest of the readout apparatus of that telescope. So far, I've suggested that casting astrophysical evidence as characteristically observational, as opposed to generated by intervention on target systems, is less helpful than approaching astrophysical evidence with the following two questions. What is the worldly target that the research seeks to investigate? And what is the data the result of causal interaction with? If the data has been produced by a causal interaction that we can trace from the worldly target using the theoretical resources of the relevant epistemic context, then I think we can call this data empirical. It could, of course, still be poor data, or it could still require much further processing to be rendered useful for the purpose at hand, but we could call it empirical. However, if construed from the perspective of the epistemic context in which the researchers are working, the production of data is not derived from a causal interaction anchored in the worldly target, as construed by that context, then the data cannot be empirical with respect to that target. Empirical data may have been procured via observation, or more generally detection or intervention, but not, for instance, by modeling or computation alone. So with this approach in hand, I would like to now turn to a few cases in order to show how this approach can generate fruitful questions that we would otherwise miss. Okay, so let's consider a specific example of laboratory-based astrophysics experiment. So the National Ignition Facility, NIF, at Lawrence Livermore National Laboratory uses a 4 megajoule laser facility to study matter in high energy density states, including, among other things, nucleosynthesis in stars and supernovae, instabilities in supernovae, opacity of stars, black hole accretion, nuclear reactions in stars, and planetary interiors, in short, astrophysics. The data gathered from NIF experiments is clearly empirical with respect to some target. It's not, for instance, like the results of a computer simulation alone, but is it really astrophysical empirical data? After all, the experiments at NIF are not performed by intervening on stars themselves. Are the scientists just wrong to call such activities astrophysical experiments? Is this just a bad joke? For present purposes, I want to focus on a particular paper from 2018. So in this paper, the authors report results from a series of NIF experiments first designed in 2009 that aim to study the Raleigh-Taylor hydrodynamical instability, which occurs at the boundary between fluids of different densities, where the lower density fluid is somehow being pushed into the higher density one. It has these characteristic kind of fingers and mushroom caps, and maybe you've seen this sort of image before, or seen it happen near coffee. So this instability is thought to occur in supernovae at the interface between the forward shock moving outwards into the relatively low density circumstellar medium out around the exploding star, and the induced reverse shock in the relatively high density expanding stellar ejecta. And the researchers wanted to investigate the possible effects of high energy fluxes on the structure of these Raleigh-Taylor instabilities in supernovae. So in particular, they were interested in the hypothesis was about the removal of material from the interface between the two shocks, where the instability is evolving under high energy flux conditions. So at NIF, this like massive laser system is focused on this tiny little horum held in place at the tip of this point. And the lasers irradiating the horum produce X-rays, which when absorbed by this package, produce a blast wave through the relatively high density plastic into lower density foam. The experimenters report on two different conditions. So they have a high flux case, which is depicted in the top right radiograph image of the physical experiment. And they have a low flux case, which is depicted in the bottom radiograph image. So notice that in the high flux case, there's no mushroom caps on the little RT fingers, and that the height of the region of mixed density is smaller than in the low flux case. So model parameters fitted to empirical data from a particular supernova, SN 1993J, suggest that the energy flux from heat conducted from the shocked circumstellar medium back into the shocked stellar ejecta are evidently larger with respect to the physical system than those present at the National Ignition Facility experiment. So insofar as the structure of the RT instability was affected in the experimental setup, the structure in the case of the supernova should have been affected too. The researchers conclude realistic models of supernova remnants must account for the effects of thermal conduction to accurately predict their evolution in epochs immediately following the shock breakout. So the question I want to pose at this point is, how do we construe the evidence generated by the NIF experiment? Is this astrophysical evidence? Is it physical evidence from which one might make astrophysical inferences? How exactly is it that conclusions about supernova remnants are supposed to have been drawn from terrestrial experiments? The short, but we'll see not quite satisfactory answer is that one can argue that the physics, the RT instabilities under the influence of high energy fluxes is the very same in both cases, such that in experimenting on X-ray blasted plastic and foam, researchers are probing the very same kind of physics playing out in distant supernovae. Sherry Rauch makes a general argument to this effect in her 2018 article titled The Epistemic Superiority of Experiment to Simulation, in which she weighs in on this fascinating debate in philosophy of science about the relationships between and proper uses of experiments and simulations. This debate has been in large part focused on whether there is anything distinctive about experiment in comparison to simulation, and to the extent that there is, whether it makes a difference to the experimental utility of the results of experiments and simulations. So to just give you a quick sense of the terrain here, one contentious point in this literature has been, for instance, whether the materiality of experiments is an epistemically salient feature. That is, whether the fact that the experiments intervene on the material systems that are the subject of scientific research is what makes experiments epistemically superior to simulations for learning about those systems. And one problem with this suggestion, which you might see right away, is that many scientific experiments do not intervene on precisely the material systems that are ultimately the subject matter of the research question, right? So consider, for instance, the routine use of animal models like lab rats to study phenomena that, of interest in humans. Right? So Rausch's take, which I think is quite sensible, is that experiments are superior to analogous simulations in cases where, quote, the outcome of the experiment is in part determined by facts that are not known to the scientists, but that do not need to be known in order to interpret the outcome as answering the set question, and that the sample and target are of a kind whose kindhood can be legitimately projected into the unknown properties that determine the answer to the question. And I take it that this sort of account is consonant with the motivation behind the NIF-RT experiments, like the utility of doing a laboratory experiment in this case, where there is a genuine open question about how the physical systems behave. How do high energy flux conditions affect the RT instability structures? A laboratory-based experiment on plastic and foam is superior to a computer simulation for learning about the astrophysical systems of interest in virtue of the fact that the laboratory and astrophysical systems are instances of a single kind with respect to relevant properties. So I take it that something like this, and Kristen, tell me if I'm wrong, is the view of physical kindhood that's also adopted by Crowther, Linneman, and Vutrick in their recent paper on dumbhole phenomena, in which they argue that analog experiments, that is, experiments for which the target system is experimentally inaccessible, cannot conform to the existence of a phenomenon of interest in that target system. Oh, sorry, cannot confirm the existence of a phenomenon of interest in that target system. So on their view, calling an experiment analog signals that the researchers are in a, quote, severely limited epistemic position with respect to the target system compared to an ordinary experiment in physics. Because they suggest that, in all cases of experiment in physics, the particular systems being used are meant to be representatives of some more general class of systems, which are supposed or conjectured by current physics to have in common some particular salient properties. So analog experimental signals, the analog in the analog experiment signals or ought to signal a kind of dignified restraint, in their words. What's missing in the analog experiments as opposed to non-analog ones is the empirical confirmation that the target system actually does belong to the relevant physical kind. So, I think they rightfully say, like, what it is to be the same kind of system in physics for a specific application is in fact determined by the reference to the formal similarity of the modeling frameworks that describe the systems under the relevant conditions. So, and indeed, this is what we see in the case at NIF. So the authors of the NIF article appeal to this paper by Raleigh-Taylor et al. That lays out particular criteria for establishing the physical similarity between laboratory conditions and those occurring naturally in the supernova hydrodynamics. And here's that paper. Here are these conditions. I'm not going to go through these in any detail. For present purposes, I just want you to notice that there's a key assumption is zero thermal conductivity. And according to Raleigh-Taylor et al., if those similarity conditions are satisfied in an experimental and a natural system, then the two systems are identical with respect to their hydrodynamical physics. And the similarity can break down when the energy flow by particle heat conduction or by energy flow by radiation flux are non-negligible. So again, how ought we to construe the evidence generated by the NIF experiments? Is this astrophysical evidence? The evidence produced at Lawrence Livermore is neither the result of observations of supernovae, nor the result of interventions on supernovae, but these issues are irrelevant to the epistemic utility of the evidence in this issue. Instead, we should ask, What is the worldly target of the NIF research, and by causal interaction with what has the evidence been produced from the perspective of the relevant epistemic contexts? Perhaps we could say that the worldly target is this particular supernova, SN 1993J, yet the causal interaction that produces the experimental data is interaction with the NIF plastic and foam, thereby ruining the empirical nature of the data with respect to the astrophysical targets. Or perhaps we could say that the NIF plastic and foam targets are the worldly targets of interest, but that would ruin the astrophysical nature of the data. But I think you can see, to recover a sense in which this experiment produces astrophysical evidence, we could adopt a Rausch or Wuttert type approach by construing the worldly target as a general class of hydrodynamical instabilities in high energy, high density states of matter. Then, insofar as laboratory systems and far away removed astrophysical ones instantiate this very same physics, that is, are of a kind whose kindhood can be legitimately projected, in Rausch's words, into the relevant unknown properties. Then investigating the effect of high energy fluxes on hydrodynamic instabilities in laboratory plastic and foam is just to investigate the very physics playing out in the astrophysical context. So NIF data are empirical with respect to high energy density states of matter and their behavior, since there is an interpretation of the provenance of those data such that they are the products of causal interaction of matter energized and confined by the NIF lasers with the laboratory detector systems, and insofar as such high energy, high density states are instantiated in faraway astrophysical systems also, the data gathered in NIF experiments can be used to constrain astrophysical theorizing. But perhaps you share a lingering worry that I have. If the argument from hydrodynamic similarity requires that the energy flow from heat conduction in the systems be negligible, but the experiment in question is designed to investigate how high energy flux from heat conduction influences the structure and the evolution of hydrodynamic instabilities, does the very aim of the experiment undercut the specified connection to astrophysical targets like SN 1993J? And if I were you, I'd probably bet on the physicist in this case, but I've emailed them just to check and I haven't heard back, but if you invite me back for another talk, I'll keep you updated on what I hear from them. All right, even if the NIF researchers are mistaken in this way that I'm suggesting, that wouldn't necessarily be a problem for the philosophical view, the Rausch, Crowther, Linneman, Wuttert type kindhood approach. And in fact, adopting this approach as a framework for analyzing the epistemology of this experiment would have helpfully aided us in discovering this kind of interesting, I think, epistemological problem. I think these are all details and problems that we would miss if we approach this as an issue about observation or intervention. So the other cases that I have for you are going to be much shorter. The second case that I want to talk about is the original result from the Event Horizon Telescope. And as I bet you know, these results come from radio data of M87 star amalgamated from these 8 stations together composing a very long baseline interferometer, which are processed using a suite of presuppositions, including the distance to M87, a geometrical Earth model to precisely locate the stations with respect to one another, a clock model to synchronize the data across stations, as well as, for instance, atmospheric corrections. The various base pairs of this long baseline interferometer system sparsely sample the radio sky in Fourier space. And from this patchy data, an image in real space has to be reconstructed. So early efforts by 4 subteams to reconstruct an image of the black hole accretion disk from engineering data yielded these 4 different images. And to the eye, I think they look quite varied. And this variation stems from different assumptions made by these different teams in the reconstruction process. So to determine how best to reconstruct the image from science data, the team as a whole tested various imaging pipelines on synthetic data for which the corresponding ground truth image was already known. And then they developed 3 different imaging pipelines, selected the top set of parameters for each of these pipelines based on their performance reconstructing the synthetic images. And then these 3 pipelines were applied to the actual science data then, quote, because the angular resolutions of the reconstructed images vary among the pipelines, we blurred each image with a circular Gaussian to a common conservative angular resolution, and then averaged together the blurred images from the 3 pipelines to produce this final image of M87 star's accretion disk that we saw on the front page of the New York Times. Right? So to test whether this reconstructed image is consistent with the expectations assuming general relativity, the image was compared with a library of synthetic images, which were generated from a library of simulations, generated from a variety of general relativistic magnetohydrodynamic models of black holes, characterized by the spin angular momentum and mass of the model black hole, and the net magnetic flux over its model event horizon. And then using these synthetic images generated from these models, the team found that the empirical image of M87 star's accretion disk, quote, is consistent with the hypothesis that it's produced by a magnetized accretion flow orbiting within a few characteristic radii of the event horizon of a Kerr black hole. So parameter values of, for M87 star were then inferred using a variety of methods. And I want to note in particular that the inferred mass of the physical black hole is arrived at by a combination of methods, including invoking these models. So in keeping with the present approach, I don't think this research is well described as an observation of a black hole, although this does generate fun news headlines about seeing the unseeable and such. You know, perhaps like detection consistent with a black hole accretion disk would be better, although admittedly less sexy. It's also clearly not an instance of intervention on a black hole. Nevertheless, we can ask, does this research yield empirical evidence regarding black holes? And I think the answer is yes. We can say that the worldly target of research is the M87 star accretion disk, and that the data collected via the radio telescopes here on Earth is empirical in virtue of having been produced by causal interaction with it. The radio telescope data is empirical data with respect to M87 star's accretion disk. However, I do want to admit here a kind of uneasiness, and maybe we can talk about this, about the empirical nature of some of the more heavily processed EHT results, such as the inferred mass of M87 star, or even the reconstructed images of the accretion disk. So in general, you know, to get an empirical result that can actually be used as a constraint on theorizing, data often have to be heavily processed and the data transformed in the process. In this case, in order to check the consistency of the radio telescope data with general relativity via these models of black holes, the data are transformed, but they're also supplemented by assumptions that help fill in the details that make a reconstruction of the full image from limited sky coverage in Fourier space possible. And this sort of supplementing is not, of course, limited to EHT images, nor to astrophysics specifically. One can find very similar examples in particle physics and climate science too. So we might want to say that these reconstructed images are empirical insofar as they are a downstream product of empirical data, but perhaps this is a slippery slope. You know, perhaps empirical data can't be supplemented in any way, in any which way, and remain properly empirical. Should an almost entirely synthetic image with a tiny patch produced from empirical data count as empirical for the purposes of testing the empirical adequacy of our theories? I actually think, at the moment, I actually think, well, sometimes, yeah, because there is no really raw data, no totally uninterpreted or unprocessed data. There's a continuum extending from lightly processed empirical results to heavily processed ones. And insofar as the processing involved consists not just in easily reversible transformations, but involves intimate integration of theoretical framings and assumptions, more heavily processed results look more and more hybrid, like the hybrids between virtual and empirical results. In any case, the epistemic utility of the empirical results depends on the details of the provenance, however processed or unprocessed they are. In other words, what a result can be used to learn depends on how it has been produced, including what transformations it's undergone and what theoretical framing it has absorbed. And this is true for thermometer readings as it is for accretion disk images. So while I think it's worth emphasizing the distinction between the purely virtual results and heavily processed empirical results on pain of falling into a kind of rationalism, Whether a heavily processed empirical result is useful for a particular epistemic purpose depends in large part on how it's been processed. Obviously, not every highly processed result, nor every way in which results may be highly processed will be useful for a given epistemic purpose. Empirical results are best construed as conditionals, I think, like, if such and such data collection conditions obtain, and if such and such assumptions are made, and if such and such processing occurs, then the result is such and so. So therefore, when we check our theorizing against empirical results, we're really checking our theorizing against empirical results together with all of this baggage associated with their provenance. And whether or not the empirical results are well adapted to what we're trying to check depends on the nature of the baggage. And in other words, the epistemically interesting thing is not that the results fail to be purely empirical, nor even how elaborately or thoroughly they've been transformed since data collection, but rather what that processing has accomplished in transforming the data. But there had better be some kind of causal connection to the worldly target of interest. So returning to the case of NIF for just a second, supposing for the time being that the very conditions of the experiment are not self-undermining in the way I suggested, I think this means that we ought not construe the results of the experiments simply as results about astrophysical targets. Rather, we ought to acknowledge the baggage that those results carry in virtue of their provenance. So in this case, that involves acknowledging that the results depend on the assumptions that the physics of the NIF plastic and foam targets is relevantly similar to the physics of supernovae. And if that assumption turns out to be wrong, then the epistemic utility of the results would need to be reassessed. And I think in the case of the Event Horizon Telescope, we can take a similar tack. So the results obtained, like the mass of the black hole is such and such, are inseparable from the baggage of their provenance, including all of the myriad techniques and assumptions that went into turning antenna data into this image. The data processing simultaneously makes possible the comparison of empirical results with theorizing, and also limits the scope of the epistemic utility of those results. Processing is what allows data to speak to theories at all, and in doing so, it inseparably endows the results thereby generated with baggage. So I just have like a very tiny thing to say on the multiverse, and then I'll stop talking. As a final example, I just want to briefly consider how attending to the distinction between the empirical and the non-empirical pertains to the possibility of empirical evidence for constraining multiverse cosmology as a kind of extreme case. So the inflationary paradigm and several of its contenders yield speculative hypotheses regarding a vast multiverse, of which our own multiverse, our own universe is only a small part. And the nature of this multiverse varies significantly according to the theoretical approach you adopt. However, even in standard cosmology, the age of the universe and the finite speed of light bounds the part of the universe that's empirically accessible to us at any given time. So from the perspective of our own physical theory, there are limits to the empirical access that we can possibly have. This isn't just a matter of parts of the universe being unobservable in the sense of unseeable to human eyes. And this isn't just a matter of being inaccessible to manipulation or experimental intervention due to extraordinary distances. The problem is deeper than that. Our theory tells us that this that is impossible by any means whatsoever to concoct a causal chain with one end in the target of interest and one end producing the data. For parts of the multiverse, or parts of a single large universe for that matter, that are causally inaccessible to us, there is simply no hope of generating the relevant empirical results. In other words, if you want a multiverse that is empirically interesting, it's got to be possible to put it into causal contact with us, according to your theory. So here's an inflation-driven story of this sort of causal contact. Suppose the very early universe is in a false vacuum state, expanding exponentially, and that small regions in that space tunnel into a true vacuum state, forming bubbles that expand more slowly than the surrounding space. If the true expansion, if the expansion of the parent space is not too vigorous, the individual bubbles that nucleate can sometimes run into one another. so the theorists tell us. And in this story, our expanding universe is just one among these bubbles, and if we're lucky, traces of collisions with other bubbles could have been imprinted on the cosmic microwave background. However, even if we're lucky enough to find patterns in the CMB that can plausibly be interpreted as a result of some collision with other cosmic bubbles, that doesn't put us in the right sort of causal contact with the entirety of the purported multiverse, right? Like, according to this story, there will be parts of the multiverse that will be forever outside of our causal context still. Just one more tiny thing. In honor of Sir Roger, who's recently been in the news, right? We could also tell the following sort of story from his conformal cyclic cosmology. So Sir Roger's story is that our own universe is just one in an endless chain of cycles that are stitched together in this very clever way. And the expansion of our universe will eventually just leave islands of supermassive black holes that will then themselves eventually evaporate. And due to the very clever stitching of the cycles, the radiation from these dying black holes would then imprint itself on the cosmic microwave background of the next cycle. And so we ought to look for relic imprints of the cycle prior to ours on our own CMB sky. And as speculative as these stories are, I think like this is the sort of theorizing that one needs to do in order to have any hope of empirical results from the multiverse, right? Of course, there are terrible practical challenges in finding features in the CMB that could be meaningfully interpreted as originating from a bubble or a cycle beyond ours. Like hunting for shapes in the CMB turns into like cloud watching and gazing at tea leaves, because you can find Stephen Hawking's like initials in it, or a little antelope, or a parrot or something if you want in there. And so you need these very clever statistical arguments to turn these whatever kind of features you find in the CMB into something physically interesting. So to summarize, I've argued that invoking a dichotomy between observation and intervention and failing to track a distinction between the empirical and the non-empirical leads to these kind of three mistaken inferences about astrophysics, which I think are just instances of equally mistaken, more general ones. And then I've argued that if we ignore the observation-intervention distinction and attend instead to the distinction between the empirical and the non-empirical, we come across deeper and more interesting questions about the epistemology and methodology of science, especially in these cases that I've mentioned. So with all this in mind, are observation and experimentation core characteristics of empirical science? And if not, what is? I think the answer to the first question is no. Observation and intervention are by and large irrelevant to what's characteristic about empirical science, though of course there are important and legitimate instances of empirical science that are indeed observations and experiments. But to answer the second question, I think that it's crucially important to keep in mind the empirical status of the evidence in focus. So purely synthetic results couldn't help us to learn about nature in the same way as empirical ones, even if those synthetic results could distinguish between competing theoretical alternatives or have many other virtues that we could talk about. The empirical part is necessary, and to be empirical is to be hooked up in the right sort of way to the target systems. So I've argued that empirical astrophysical evidence must derive from a causal chain that has one end anchored in the worldly target of interest, and that construing the issue in this way allows us to ask more nuanced questions about science and practice than we would in the normal framing. And I hope to have convinced you that by emphasizing the distinction between the empirical and the non-empirical, we do better at tracking what's significant about empirical science in the first place than we do by embracing like linguistic contortions needed to continue to use terms like observation and intervention and experiment in much of contemporary scientific research. Thank you.
Thank you very much. Okay, let's start the discussion We have about, I think, a little bit more than half an hour, 35 minutes. So who would like to ask a question? Please try to get my attention. I see there's Mike.
Hi, Nora.
Hi.
I liked this a lot, and I'm totally prepared to be on board with your main thesis, and I want to try to push it into this realm that you were getting to at the end, where can we use this account to put pressure on certain forms of speculating as going to be particularly ill-suited for empirical investigation compared to others. And specifically, I was very interested in the upshot of tying a conception of empirical research to causal chains in situations of cosmological interest where, well, causal chains are, as we usually think of them, embedded in the world, and so we can start generating counter cosmological scenarios where the chains themselves aren't in the world that we're talking about. So in particular, tachyonic theories, I would think, have this quality, but same with, say, Newtonian cosmology, where we don't have the convenient light cones bounding everything that we're going to treat as causal or participants in the causal chain. And so I was wondering if I could get you to just walk me through a bit more of your view as applied to these sort of pernicious causal chains.
Yeah, I don't know how much I'm going to be able to say to satisfy you. I think it's a really good question. I mean, I know enough from sitting in seminars at Pitt and at Irvine that that like what causality is in relativistic cosmology is already tricky. And I just remember like being in Valente's class where we had these long discussions, and Erman was there, and it's like, how do we even think about this stuff? So I think what I need is for all that to come out in the weeds, like within whatever theoretical framework you're working in. So I think like what I would want to see is just, your epistemic context, your theory owes me some story about how the data is produced by causal connection with its target within using the resources of your theory. So, and I'm fully happy for that to look really different in lots of different theoretical contexts. I mean, I kind of came across this a little bit in thinking, I have no idea what Penrose is talking about with this CCC stuff, because I like, first of all, I don't understand like what the physical story is supposed to be about matching the, I mean, he like in some of these, he has a recent paper with co-author Anne, I guess, at the beginning, and the hand wavy stuff that happens at the beginning of the paper to give some kind of physical motivation for stitching, for doing this mathematical move of stitching these cycles together seems very sketchy to me. So I think like, I'm not sure that I can get on board, very far with this, with this particular story. But I think if you, in this example, even, it's like, well, it kind of looks like, everything's causally connected, right? Like, there's no way of not being in causal contact in this universe. So it's kind of like, I don't really know what to do with that, but I think probably where it breaks down is like in the earlier part about the physical story and in matching these surfaces. So anyway, but what I'm trying to say is I think these conversations are going to get like very strange and interesting for fancy cosmologies about the causal question. And I think that the only thing to do is just to like dive in and try and figure out what causation looks like, what connection connection looks like in those worlds. But, yeah.
That's great. Thank you.
Thanks. Alan.
Nora, I think you're absolutely right to emphasize the question of the quality of evidence, namely including both the analysis procedures, the raw data, as well as the theoretical context. I don't think myself, I've never had any cash value for the distinction between experiment and observation. I mean, for example, does deep inelastic scattering of electrons or protons interact directly with the quarks? I have an old paper a few years ago on direct and indirect observations, which is better? And the answer is, well, sometimes one is better. You know, I don't have a scheme, but I think the question is, how do you evaluate the evidence? That's the word that's really important in talking about empirical science.
Mm-hmm. Mm-hmm. Yeah, and I think we probably agree that, you know, whether some empirical result is going to do what you want it to do for some purpose, you know, it depends on what the purpose is, what you're trying to do, how it's been produced, what has happened in the processing, you know, all of that work that's gone into the production. You have to pay attention to that in order to know if you're getting at what you're trying to get at. You know? Yeah.
Okay, John.
Sorry. Hi. This is really cool, and I thought convincing, and especially like in light of the example, super convincing. I want to ask a question which I think might just be to say more about the paper of yours that you referenced. So your criterion for when data are empirical is relative to the target and the epistemic context. And it's important that the data be causally connected to the target. So my question is, can you say something more? I mean, I assume it's not just like any old causal connection. It has to be sort of connected in the right way, where the right way means something like the data answers the questions that you care about in this context or something. So the specific kind of worry that I have, or like thing I don't know how to think about, is in these high energy experiments where like sort of what counts, it's hard for me to separate the context from the data, because so much of the data is shaped like from the beginning by simulations and cuts and things like this. And so, you know, I guess the question is, how separate does the epistemic context need to be from the data for it to count as empirical in the right way?
Yeah, probably. I mean, like probably not very. I mean, I think you can you can do bad science in the sense of making assumptions early on that prevent you from getting epistemic purchase on the thing that you were interested in. You can blunt your empirical results so much that they can't answer the question that you were interested in answering. They can't constrain your theorizing in the way you had hoped. But I think that we should get rid of this idea that you know, involving theory in data processing and data production is somehow tainting the empirical nature of the data. You know, insofar as there's any involvement from theory at all, I don't think that that's a very helpful view, because we can find lots of instances where, you know, even instances where the very theory to be constrained is being involved, you know, very early on in data production and processing, but in a way that doesn't, you know, poses no problems for the epistemic payoff of that research. And, you know, I think that this is really interesting because I think for a long time philosophers of science were like, oh man, theory leadiness is bad and we have to really keep track of this. And if you know, observations are theory laden, then they sure as heck shouldn't be theory laden by the very theory you're trying to test. And I think it actually just turns out not to be the case. And in fact, sometimes it's very useful to involve assumption, the modeling framework or assumptions from the very theory that you're trying to test very early on in data processing, because that's what ends up allowing you to put the empirical results in contact with the theory in the right sort of way. You have to sort of like package them up in that very framework in order to get them to compare to the theory that you're trying to compare to. So I think I don't think there's a whole lot that I could say like in general about this, except to be wary of, you know, claims that any theory ladenness is bad or theory ladenness by the theory that you're trying to test is bad. I think you just have to check to see have the assumptions that have been made, the modeling assumptions, the data processing, has the way that theory has entered into the production of these empirical results gotten in the way of the thing I was trying to do. You know, merely the introduction of such things is not going to guarantee you that that's going to happen. So, yeah. I mean, I think there are these. I would really want to spend, you know, more time thinking about the high energy physics cases, because there, you know, there in that context, there are a couple spots that like make me a little bit nervous, where like you know, the only way to get the right backgrounds to subtract from, you know, the data that you're interested in are to simulate that we can't, because of the nature of the physical process involved, we can't get we can't just go out and measure those backgrounds. We have to rely on, so there, you know, there are these really, you know, these kind of hybrid looking cases where it's like, this thing is an amalgam of empirical stuff and synthetic stuff. And I think where I'm at right now with this, but, you know, feel free to push me in different directions here, is like, I think, you know, I was trying to say this in the top, like, I think when we think about it, we're actually always in this situation where our empirical results are almost always processed in some way, and we're never pure in the first place. And so what really matters is not that they're amalgamated and hybrid and processed. It's that we have to keep track of what that processing has done to the results in order to make sure that we're not blinding ourselves to the thing that we're trying to do. So the paper, this philosophy of science paper that I was pointing to from 2018, the argument there is really like, look, we've made the mistake in philosophy of science of thinking of evidence as either the raw data, which there is no such thing, or as the empirical result at the end of the day, like the parameter value. And this is not what empirical evidence is. The thing that constrains theorizing is actually like that whole story about how the data has been processed and all of the information about what's gone into it. Because you can't, you need to keep all of that in mind in order to judge whether or not, you know, the constraint that you're trying to get at is actually happening in the work that you're doing. So, but yeah, I agree that like the HEP stuff makes me nervous too. There's some climate cases that also make me nervous too, and it has to do with this, like when we interpolate, you know, when we make up fake data to fill in stuff. And I kind of, and so on some days that makes me more squeamish than others, but I think that if we just, you know, keep track of what we've actually done and not kid ourselves about what, you know, what has been what is coming from nature and what's not, then we should be able to use those kind of hybrid results strategically and intelligently, and not like not get confused and think that you know, oh, we might as well just use simulations instead or something like that, which I think would be the wrong way to go. So
Yeah, awesome, thank you. Yeah, the background stuff is exactly what was puzzling me, and so that was super helpful. Thank you.
Okay, great. Lorenzo.
Before my question, I had just a comment on, I think was the second slide, or maybe the third. Was a quote on
this one?
Exactly, yes. And I think a very important thing to note is that I suspect that this physicist is one of those people that uses the word literally to mean figuratively, because however you interpret to observe, the computer is not giving us a window.
Yeah, I agree. I you know, I'm not a pedant, but at the same time, like, that's a bad use of the word literally. It's a way to make philosophers confused. I
think Orwell said that bad speakers are indifferent to the content of what they're saying. It was a very actual question was, I mean, I also think what you said is very plausible, but I am worried about one problem. So what do you mean by the target system? So I suppose that if you want to study, say, neutron stars, then your targets, you have many targets, but there are only, say, a fraction in which you are in direct causal contact with, or the data have been produced by only a fraction of them. And then you need some induction step, some way to infer that, I've observed this about this particular objects, and then I need to infer something about this wider class of objects. But then the question is, why can we exclude then these for simulations? So if we say, well, they belong to some more inclusive class that contains both simulation and the targets, and then by inference, but by looking at the simulations, I can infer something about also the unobserved cosmological objects, or say the astronomical objects. Why is these two processes different on your account?
Yeah, I've definitely been asked this before, which is like, what if the simulation, like, functionally instantiates the relevant physics, why doesn't that count as belonging to the proper kind? Yeah. And I'm still not sure if I have a good answer to that. So I think that the even sort of trickier case is, like, suppose we have empirical initial condition, like data that we're feeding into the simulation rather than starting from a model that we're then running simulations on. Then it looks even worse for me. It's like, well, then that just kind of looks like processing, on empirical stuff that I've already said is empirical. So why shouldn't that count? And I think maybe in that case, I have to bite it and just say, yeah, these look like horrible hybrid results, but really that's what's happening with all of our results. So we shouldn't. It only looks scary initially, and we should just accept that these are still empirical, just highly processed, and just keep track of everything. But the case of, like, yeah. So I don't know. Maybe you can help me with this. I mean, I think at root, I think I do at the moment, and I wish I had a better justification, but I think I do at the moment just kind of have a this bottoms out for me in a sort of, look, it's worth keeping track of a distinction between an empiricist philosophy of science and a rationalist philosophy of science. I think there's a meaningful distinction there. If we could do we would live in a very different epistemic world if we could just do science by thinking. And I think that if we're talking about purely simulated results, that's where it bottoms out for me. It just doesn't. It's no longer empirical science. It's not doing the sort of thing that we need empirical science to do. And what I've been trying to do in this talk is like say more about like what makes empirical science empirical, because the kind of historical take has been, well, it's about observation, or if it's not about observation, then it's about experiments and intervention. And I'm saying like, no, it's not those things. But I think there is still something at the end of the day worth keeping track of. But to have some kind of distinction between empiricism and rationalism. And I think that if we're allowing results that aren't informed by the natural world at all, then we're just doing the rationalist thing. Now you could come back and say like, well, nobody does simulations just ab initio, like they're informed in some way by nature. And then I think we could have maybe we'd have to get into the details more about the particular kind of case that we're thinking about, because that might just turn out to be kind of like the other case that I mentioned, where we're feeding in, we are feeding in appropriately empirical data to it. So it is going to count on my view as just highly processed empirical data, and then I may be willing to admit it into my view. But I think the thing that I want to exclude is just like, the thing that doesn't, you can't connect back up to the world in any way, and maybe nobody holds this view. Like maybe there are no such rationalists. I think you're right to point out that this quote is like probably just bad grammar or something. But it makes me nervous enough to want to like police that boundary a little bit, don't get, let's not forget that there is actually something worth keeping this thing to.
Yeah, but I wasn't saying there is not something worth drawing the boundary. The problem is I'm concerned how to do it to my satisfaction, and I'm not sure. I mean, you have something nice, but there's still something I cannot see.
Yeah.
Okay. Great. Julius.
Hey, Nora, thanks for the great talk. That's really fun. I particularly like how you stressed that sort of our conceptualization of what the target is matters. And I think that's a particularly good point in the context of EHT, which we can see as the sort of evidence for interesting and fun accretion astrophysics. And then I think you're right in identifying the accretion disk as the sort of target of the observation. But we could also identify the whole source, not just the accretion disk, but the whole source, like including the black spot in the center as the target. And that would work slightly better that would be maybe a better choice if we thought of this observation as something like a test of the Kerr paradigm for black holes or something like that. And of course, depending on which particular thing I'm interested in, the choice of particular target will be slightly better. Like some people in the collaboration seem to be very excited about tests of the Kerr paradigm, and some other are more cautious and say, well, what's really exciting about the EHT is the new window for accretion that we get with this. And so I guess my comment is that this seems to nicely sort of fit into the scheme that you propose. And another way in which what you say maybe sort of fun or perhaps a little elaborated is that at least under this more narrow conceptualization of the EHT target, with the subsequent observations, the target itself may evolve. So perhaps a good case could be made that the actual target now is just the accretion disk, but perhaps with the subsequent observations, like for instance, if we do ever, as a humanity, kind of grow up and get the antenna for the HD at L2 or something like that, the target could somehow change and expand and include other parts other than the accretion disk, but also something like near horizon structures.
Yeah, cool. And I think it's, I think it would just be worth keeping track in that evolution about, what is really being constrained there, and where the data is really coming from. I mean, I think that I don't know, I haven't been following all the black hole information loss stuff that's been happening in the news recently, and you all can tell me about that. But like, I mean, it's cool if there's, more phenomena at the horizon that could be studied empirically. The problem with black holes, we can't get, causal information directly from that target, and so yeah, I mean, I'll probably get out of my depth fairly quickly here, but like, I think
it's not really a point about the information loss, because that seems to be inaccessible with this sort of source, because the accretion will clearly dominate the depending on what part of the information loss you want to study, but that I think is more like a dream, right? To be able to study these processes with like EHT type observations, and we're very, very, very long way from that. But
you're talking about like higher resolution.
Yeah, exactly. So depending on, I imagine that depending on what I think to be a target for the observation, changing the resolution may also lead to change of the target. And it is this more restrictive aspect that I had in mind when I said about like further resolution increased EHD.
Yeah, that makes sense. And I think we see that probably in a lot of areas in scientific research where, the advent of new technology or new methods or new access to space, in this case, would open up new targets that wouldn't otherwise be accessible as a practical matter. Yeah, and yeah. That's very cool. I didn't know that was in the works.
Okay, Mike?
Yeah, if I could hop back in again. This question came to mind based on how you were responding to Lorenzo's question, reintroducing just empiricism versus rationalism as sort of the playground. And I'm wondering why I can't think of the pure simulation scenario as like the idealism version of empiricism in this conversation, where somehow all of the practice that I'm engaged in building this, castle in the sky simulated, I'm doing it all to try to cognize these things that I take there to be in the world on the basis of these causal chains that start with the worldly targets and end with me. And so, is this available, and you just didn't take this route, or is there something wrong with that perspective?
So, are you thinking of there's a mode of scientific research where we do a lot of work without looking at nature at all and explore the contours of the theory, figure out what its possibilities are, where it breaks down, what learn very intimately what the features of a theory are by exploring it world entirely aside. And I think that that's like a really interesting and useful thing to do to intimately understand our theories. And that's, properly part of what scientists do. But I think that, ought not be confused with this other really important part of science where, if we're interested in whether or not those theories are good representations of the natural world, we have to go and inquire of nature whether or not they really are. And it's at that stage where the empirical aspect of the results is essential, that we can't get around it. We can't ask nature in another way.
I think this is the right setup for my question. Right? So on the side of the science that is trying to fully explicate what it means to wield said new theory that has just been written down. But it seems super important in that process that I already lay out my commitments about who the observer is in the world, privy to the results of the world being governed by said theory. And that already seems so close to the conversation that's going to go on the empirical side that I'm just wondering, isn't it close enough that this is the pure empiricism element of it, and that's why I was saying idealism, where this is me fully immersing myself in the question of what is the empirical world on assumption that it is exactly according to this theory.
So, I mean, you can ask the question, what empirical results should I expect to see if this theory is true of nature, right? And that's something that people do all the time. You still need to go out and check whether or not that's the case. I thought you were talking earlier about, the question of whether or not elaborating a theory from the perspective of a particular kind of observer would already count as empirical enough. And I don't think that that's the case. I mean, I don't know, maybe I'm just, because I just read this, the Dumbholes paper by Butrick and friends recently, but I'm thinking, they make this really nice point in that paper that we all talk about Hawking radiation, but whether or not you still have to go, you basically still have to go check to see whether or not Hawking radiation obtains in the actual astrophysical black holes. It's not, I mean, this is going to be incredibly hard to do, but just, it's not enough to be able to tell the story about how, black holes are these kinds of entities, and on our theory we would expect that they should radiate. And it's that's all well and good. But the whole question is whether or not, the actual things in the world do this thing that our theory says that they will. So there's still this step that that needs to happen at the end of the day. But
I guess my question is really on the carving up of the world that is involved in stating that it is a worldly target. That seems to me like that's one of the projects of pure simulation work on this setup, where we're getting comfortable with what it means to manipulate just this, in the simulation version of the world, what it means to manipulate just this part, so that we are comfortable when we turn to the real world, saying that there is a part that is the worldly target, separate from the sort of manifest world of experience. But I'm not framing the setup in a clear way. I still want to say even the pure simulation stuff as think I'm following the account you're laying out, it does wind up as sort of satisfyingly empirical.
It's somehow empirical. I think we'll have to look at it in more detail. I mean, it seems to me like you can do a lot of investigation and simulations and have a lot of expectations about how the world would behave. And the problem is that it doesn't always go that way. So it might be that, the way you've decided, the way that it works in your simulation to carve up nature, seems like it has everything going for it. And then when you try and apply that framework to the actual world, things break down, you get all kinds of problems, and it turns out not to be a plausible way to go. And so I don't know, but I think it would be interesting to Mike, to look in more detail and talk more together about like what sort of simulation you have in mind and what kind of cases, because I'm curious for sure.
Okay, Richard.
Thank you. I really enjoyed your talk and I love the examples, but I had a question about targets. And your first example, it struck me that what you said about targets wasn't what I initially thought you were going to say. In that example, it's pretty clear that what we might call the epistemic target is supernovae. But the experiment at the National Ignition Facility seemed directed towards a different target, lumps of foam or whatever it was that they were zapping with their lasers. And you wanted to somehow put that to the same kind as supernovae. And that didn't seem to me the natural way to go. Why couldn't you do this instead? Why couldn't you say that the empirical target is not the supernova at all in that experiment? The empirical target is the lump of foam or whatever got blasted in the National Ignition Facility. And that information from that, empirical information, was used in a significant chain of inference that was eventually directed at the real epistemic target. And those inferences will be mediated by theory and laws, models, whatever. But that seemed to be a better way of handling that example within your framework to me. So I wondered how you would react to that.
Yeah, I mean, I think just sort of descriptively looking at what these researchers, were saying that their reasoning was, the way that they were portraying their reasoning was to appeal to these higher level arguments, to argue that the appropriate similarity conditions were met in both the laboratory conditions and the astrophysical conditions, such that the very same physics obtains. So that in both cases, we're talking about, in this case, I mean, literally the same, like hydrodynamics of high energy, high density states of matter. And that for the purposes of this experiment, for this particular research context, the material details, the actual, the huge differences in scale, and many other things besides don't matter for the phenomena that they happen to be interested in this case. And I think that I think there are other cases in physics that work like this too, where we see for some research question the very same physics instantiated in lots of different kinds of systems. And so I think if that argument actually goes through for this experiment, it's a very strong one. So you don't need to kind of take on the this like epistemic risk, these this kind of inferential debt in a long chain of reasoning that would get you from plastic and foam to supernovae. if it works, it's very clean because it really is the same physics. So I think that, that's not only like that's in fact how the researchers were trying to justify their work in the paper that I looked at, but I think it's also a very nice way to go if you can do it. The problem is that I think that it seemed to be, at least, that it broke, the conditions of the experiment broke that nice higher level argument that they were trying to invoke there. But
this may not be a substantive disagreement, because when they and you talk about the same physics, I'm taking that to be a claim that's backed up by all of the inferential moves that you need to connect what I'm calling the epistemic target to what I'm calling to what I'm calling the empirical target. So it's just a way of redescribing it, perhaps. But I did think there was a disanalogy between the first example and the other two, where it was quite clear that both the epistemic and the empirical target were out there in astrophysics land.
Yeah, it sounds possible to me that if we sat down and looked at it, that we'd just end up writing down the same things in order to make this argument from the laboratory context in order to get to the astrophysical case. Although,
but do you see any disanalogy between that case and the other two?
Yeah, I mean, I think it does raise this question of the difficulties that you can run into in getting external validation for an experiment in physics, because it's a case where it seems on the face of it so striking that these are different targets. So I think it's a case where we very clearly owe some kind of argument about how the same physics is instantiated. Whereas in other cases, that kind of argument might be more implicit, maybe it's still there, but it's not quite as striking that the argument is needed in the first place.
Yeah, if you're going from a few neutron stars that we've actually studied to the class of neutron stars, that doesn't seem to be a big leap. Whereas this is a lot further.
Yeah, you definitely need some argument for this one.
Okay.
Yeah.
We're actually out of time, but we have two people in the queue, and I would like to give them the chance to ask a brief question. First will be Ravad, who unfortunately does not have a camera. Ravad, please.
Yes, hi, thanks. I don't know if you can hear me well, but I'm having problems with my laptop lately. Is it good?
It's okay.
Okay. I was wondering about when you were talking about science without data, and you cannot do this with simulation. So if you don't have any data coming in, then it's purely synthetic. I totally agree with you, but I was wondering if you're not just focusing on confirmation and not the other way around. So if you want to talk about maybe disconfirmation and putting your theories together in such a way to see if they are consistent together or coherent together, maybe simulation and thought experiments and models that interact with data can be helpful here. Or do you mean that as well? That's not it.
But I don't know if I heard the crucial part well enough. So you're suggesting that we use that there's a role for simulation, a legitimate role that in disconfirmation. Can you say that part again?
Yes. In such a way that these simulations of those experiments doesn't have any interference. Maybe I have a bad connection. I'm sorry.
Sorry. Can anyone else? I'm not sure I got it.
No, I'm sorry. I don't hear what seems to be the relevant part. Ravad, do you want to give it a?
Yeah, I think I'm having problem with my connection. You can skip my question. Maybe I'll send it in the chat.
Thank you. Sorry.
Yes, you could write it in the chat.
Sorry, I have a few minutes left. Bye.
Okay. Final question then, Mauricio, please.
Hello. Hi. Can you hear me?
Yes, Mauricio, you've already seen this talk, so you can.
I've seen versions of this talk, but this is a new version that I have not seen yet. In fact, something occurred to me listening to this version of the talk that hadn't occurred to me before, and I wanted to suggest that you may want to look into the literature and inference to the most probable cause. It's a kind of offspring of the literature on experimental realism, and it didn't occur to me when you gave a prior version of the talk in Madrid. It's occurred to me now in your response to some of the questions. This may be helpful because there's an argument there for drawing sorts of inferences on the basis of causal presuppositions that are then they get vindicated through experimental work, and they use the same kind of chains of reasoning on the basis of causal relations, and you may find that that it is helpful for you to look into the literature to answer some of the questions you've had.
Mm-hmm. Thank you. Yeah, I mean, I think part of the thing that would, something that would come out if we talked longer about all of this is that I'm going to be much more of a kind of strict empiricist than a lot of you want to be. A lot of you are interested in more of a kind of realist. I mean, I'm an empiricist in two senses, like an empiricist in the sense of being, in opposition to rationalism, but also in the sense of being an anti-realist. And so I think for those of you who are particularly interested in confirmation and in kind of more or less warranted inferences, this, eventually this would come out in the wash that like, that actually, I don't think that I don't think we can actually get that sort of thing. And that I think that we're actually just in the business of, checking the empirical adequacy of our theories, and that I'm kind of with von Frossen on that part of the story, except that I think that what he meant by empirical adequacy is the wrong thing to mean, but that all requires a lot more argument on my part than would have come out here. Yeah.
And I'd just like to point out that may be all consistent with some of the things that people who defend these sorts of inferences do. So it may be worth looking into that. Anyway,
cool,
great talk. Thanks a lot. Good to see you.
You too.
So that brings us to the end of the talk. It's also the end of the semester for the Beyond Spacetime seminar conference theories. So we will not have any further ones this year. We will continue next year, of course, and will announce in due course the program. For one last time, please join me again in thanking Nora for her wonderful talk. Thank you.
Thank you so much for having me, Chris, and everybody. It was wonderful to see you all.
So thank you very much, and happy holidays to all of you, and end of year festivities. Be safe, stay healthy, and I hope to see you all soon. Bye. Bye-bye.